Welcome to the deep dive. Whether you're listening on your commute or, just hang around the house, we have an incredibly fascinating stack of anatomical and physiological notes to unpack today.
We really do. It's a great topic.
Yeah, and our mission for this deep dive is to completely transform how you understand a word you probably use,
Yeah.
like all the time, which is inflammation.
Right, because it's such a common term.
Exactly. Because
Yeah.
usually when we talk about a medical diagnosis, there's this expectation of precision, right? Like engineering or something. You break your arm, the x-ray shows that jagged white line, and the doctor just points and says, there it is, broken.
Yeah, and it's a comforting way to look at medicine, honestly. I mean, we inherently like things to be binary, visible, and neatly categorized like that.
But then you step into the world of inflammation, and suddenly that x-ray machine is, well, it's kind of useless. We're looking at a diagnostic landscape that feels incredibly murky.
Totally.
Right. Like if you roll your ankle on a hike and it swells up like a balloon, you just think of it as this annoying symptom ruining your weekend. But looking at these notes, for most of human history, doctors were completely wrong about what inflammation actually is.
Oh, completely wrong.
They were relying entirely on what they could see on the outside of the body, just completely blind to the fact that there is this highly orchestrated, microscopic battlefield raging on the inside.
And the paradigm shift here is massive.
Yeah.
Inflammation isn't just a symptom. It is the innate immune system's primary tool.
This primary tool.
Exactly. It basically operates as a fast, non-specific first line of defense. So what you're experiencing as a swollen ankle is actually a highly coordinated microscopic alarm and repair system.
Okay, let's unpack this.
Yeah.
Because I find it wild that our baseline understanding of our own bodies took nearly 2 millennia to update.
Yeah, it took a very long time.
To really grasp this modern cellular alarm system, we have to start with the historical blind spot. I mean, we're talking about generations of people who were just guessing at the bedside before a few rogue scientists finally looked under the hood.
Right, they had no way of seeing what was actually happening.
So right off the bat, our notes take us all the way back to the Roman Empire. Around 30 CE, there's this Roman encyclopedist named Celsus. And he wasn't even a physician scientist, just a guy compiling the medical knowledge of the time.
Just a really good note taker, basically.
Yeah. And he gave us what are still known as the 4 cardinal signs of inflammation. Rubor, which is redness, tumor, which is swelling, calor, heat, and DeLong pain.
Redness, swelling, heat, and pain. I mean, it became the ultimate medical checklist.
Still is, right?
Pretty much. And later on, a 5th sign was formalized, functio laesa, or loss of function. Historians sometimes debate if the Greek physician Galen first noted that one, but it was the German pathologist Rudolf Virchow who truly cemented it into the literature in the 1800s.
But that's just a list of things you can see. For almost 2,000 years, that was the entire definition of inflammation. It was purely descriptive.
Right, they were just describing the aftermath.
Yeah, medicine had no idea how the redness got there or why the swelling happened. It wasn't until 1867 that the game fundamentally changed, thanks to a student of Virchow's named Julius Cohnheim.
Cohnheim is a huge figure in this.
He is. He essentially decided to stop looking at the skin and start looking at the plumbing.
And his methodology was groundbreaking and because of its sheer practicality. I mean, Cohnheim took the thin, transparent tissue of a live frog's mesentery. That's the tissue that anchors the intestines, as well as its tongue.
A live frog?
Yes, a live frog. He put that living transparent tissue under a microscope and then introduced an injury. So for the first time in human history, someone directly observed blood vessels reacting to trauma in real time.
I love this visual. For almost 2,000 years, medicine was basically just standing on the sidewalk reviewing the aftermath of a car crash. And Cohnheim finally installs a microscopic traffic camera to watch the crash actually unfold.
That analogy perfectly captures the leap in understanding. It really does. Because through that microscope, Cohnheim watched the blood flow literally slow down in the vessels near the injury.
Just slow right down.
Yeah, and he saw white blood cells drift to the edges, start to roll along the vessel walls, stick to them, and then actively squeeze themselves between the cells of the vessel wall to get out into the surrounding tissue.
Which we now call diapetesis.
Yes, exactly, diapetesis. And by watching that physical movement, Cohnheim proved that inflammation is fundamentally a vascular event.
Not a humor imbalance.
Right, it wasn't some mysterious, invisible imbalance of bodily humors like they thought for centuries. It was a reproducible mechanical process involving blood vessels.
But Cohnheim only had half the puzzle, right? Because watching the cells leave the highway Doesn't explain what they actually do once they get into the neighborhood.
Exactly. The traffic camera only shows so much.
Right. And that brings us to a few decades later and this beautifully charming accidental discovery by Elie Metchnikoff.
Oh, this is a great story.
It is. So he was a Russian zoologist working in Odessa. He's studying these transparent starfish larvae, and one day he just sticks a rose thorn into one of them and leaves it overnight. Which, first of all, why a starfish larva?
Well, transparency is the key there, just like Cohnheim's frog tissue. Metchnikoff needed an organism where he could see the internal structures without killing it or dissecting it.
Oh, that makes sense. So he sticks this thorn in, leaves it, and the next morning she looks at the larva under the microscope. And he sees that the rose thorn is completely surrounded by these mobile amoeba-like cells.
They're just swarming it.
Yeah, they're actively engulfing the thorn, trying to eat it. So he realizes these cells aren't just passive bystanders drifting in the fluid, they are active defenders.
Which was a massive revelation.
And he coined the term phagocytes, which is Greek for devouring cells. So Cohnheim showed us the blood vessels reacting, but Metchnikoff proved that inflammation is also a cellular event.
And that specific realization triggered one of the fiercest founding debates in all of immunology.
Oh, really? A debate over that?
Oh, huge one.
Yeah.
At the time, the dominant view in science championed by prominent researchers like Paul Ehrlich was the humoral antibody theory. They believed that antibodies floating in the blood serum were the body's primary defense.
Says the antibodies.
Yeah. In fact, many in that camp thought white blood cells might actually be spreading disease, acting as transport vehicles for bacteria rather than fighting it.
Wow, so it was a massive scientific turf war.
A very bitter one. It delayed the broad acceptance of Metchnikoff's phagocyte theory for over a decade.
That's wild.
But the ultimate resolution of that debate is quite poetic, honestly. As the science advanced, we realized they were both right. The system is collaborative.
They work together.
Yes. The antibodies from Ehrlich's theory act like chemical tags, sticking to the invading pathogens. And Metchnikoff's phagocytes recognize those tags, which allows them to devour the targets much more efficiently. They actually ended up sharing the 1908 Nobel Prize for this realization.
That is poetic. Okay, so we've got the traffic cameras installed. We know the devouring cells exist. But Metchnikoff's phagocytes don't just magically teleport from the bloodstream to a rose thorn or, a splinter in your finger.
Right, they have to navigate there.
Getting them there requires an incredibly complex relay race. And looking at these notes, it seems like every single step in this physiological cascade exists to solve a specific physical problem created by the step right before it.
Cause and effect. The entire inflammatory response is a domino effect of cellular problem solving.
Let's walk through this because the sheer engineering of our bodies is just mind-blowing. The very first thing that happens, the thing that kicks off the whole relay race, is the tissue's 911 call.
The recognition phase. So the moment you get a cut or a burn or a microbe breaches your skin, resident immune sentinels, called mast cells, along with the damaged tissue itself, they panic.
They sound the alarm.
Exactly. They release a massive localized burst of chemical alarm signals into the surrounding area. If you've ever taken an allergy pill, you're familiar with one of them, which is histamine.
Oh, sure. Histamine.
But there's a whole cocktail of chemicals, including prostaglandins, bradykinin, and complement proteins.
So the chemical alarm is ringing in the tissue. But the reinforcements, the white blood cells, are rushing by in the bloodstream. How do you get the blood vessels to respond to a chemical in the tissue?
Well, that's where the plumbing changes.
Right. The notes say the histamine and prostaglandins act directly on the smooth muscle wrapped around the nearby arterioles, the small arteries. They tell that muscle to just completely relax.
Just let go.
And when the muscle relaxes, the blood vessel widens. It's called vasodilation. And suddenly, a massive rush of blood floods the immediate area.
And this is exactly where ancient observation meets modern mechanics. If we think back to Celsus's cardinal signs, that sudden localized flood of warm blood is the direct physical cause of rubor, the redness, and calor, the heat.
So that explains 2 of the 4 signs right there. But opening the floodgates creates a new problem. You have more blood, but the white blood cells are still trapped inside the pipes.
Right, they're stuck in traffic. So the body solves this by changing the structure of the pipes themselves.
How so?
The same chemical signals that cause the vessel to widen now instruct the endothelial cells. Those are the cells lining the inside of the capillaries to physically contract and pull apart from each other just a tiny bit. The tight junctions between the cells get leaky.
And when the pipes get leaky, plasma, which is the fluid part of your blood full of proteins and antibodies, starts seeping out into the surrounding tissue.
Exactly. The fluid rushes in.
Wait, I want to pause here.
Okay.
If fluid is pouring into the tissue, that fluid accumulation is tumor, the swelling.
Right, the third cardinal sign.
And I need to push back on the concept of pain the duller for a second, because I'm reading the notes on what this swelling actually does.
Okay, go for it.
It says the swelling physically presses on nearby nerve endings, and at the exact same time, chemicals like bradykinin and prostaglandins are directly binding to those nerves, actively sensitizing the pain receptors.
They are, yeah.
So the pain isn't just coming from the cut itself. The body is intentionally making it hurt more by pumping the area full of fluid to press on the nerves, while simultaneously making the nerves more sensitive.
That's exactly what's happening.
Our body is basically weaponizing pain against us to force us to protect the injury.
It sounds cruel, but you are hitting on the exact mechanical purpose of pain in this scenario. It feels awful, but it is a brilliant evolutionary tactic.
I mean, I guess it works.
It works perfectly. By making that area hypersensitive and physically swollen, the body is forcing you to favor that injured ankle or keep that cut finger completely still. It's localized, forced immobilization.
Because if it didn't hurt.
If it didn't hurt, you would keep using the tissue and disrupting the microscopic repair work.
That is incredibly manipulative of my own physiology. But, I have to respect the hustle.
It's very effective.
So we've got the alarm, the rushing blood, the leaky pipes, the swelling, and the pain. The stage is set. Now we need the troops.
Right, the cells.
We need to get the white blood cells out of the rushing blood and into the battlefield. This is what Cohenheim was watching in his frog.
The cellular recruitment phase. Modern cell biology has finally filled in the molecular details of what Cohenheim saw. As that blood flow slows down in the widened, leaky vessel, the white blood cells, specifically the first responders known as neutrophils, start to drift away from the fast-flowing center of the bloodstream.
They move to the edge.
Yeah, they move toward the outer walls of the vessel, a process called margination.
But I'm trying to picture this mechanically. Blood is a rushing river. Even if a neutrophil drifts to the edge, how does a single cell just stop against that current?
It uses molecular Velcro.
Velcro.
Basically, yeah. In response to the initial 9/11 chemical alarm, the cells lining the blood vessel walls push tiny sticky proteins up to their surface. These are called selectins.
Like speed bumps.
Very sticky speed bumps. As the neutrophils rush by, they catch on these selectins. But the blood is moving too fast, so the bond breaks, then catches again, then breaks. The neutrophil starts literally tumbling and rolling along the inner wall of the blood vessel.
Oh, wow, they're tumbling.
Yeah. And as it rolls, it encounters a second, much stronger class of adhesive proteins called integrins. When the neutrophil hits the integrins, it locks firmly into place. The rolling stops.
The parking brake is pulled.
Completely locked down. And once it's anchored, the neutrophil performs diapedesis. It flattens itself out and physically squeezes through those tiny leaky gaps between the vessel wall cells that we talked about earlier, exiting the blood vessel entirely.
Okay, so they're out of the bloodstream and into the tissue. But how do they know where the actual splinter or bacteria is? I mean, it's dark in there.
They follow a chemical scent trail. Those initial alarm chemicals, the chemokines, are most concentrated right at the site of the injury.
Oh, like a gradient.
Exactly. The neutrophils are covered in receptors that can detect these molecules. They literally crawl up the concentration gradient, moving from areas of low chemical concentration to high concentration until they reach ground zero. This tracking process is called chemotaxis.
It's like microscopic scent hounds tracking the alarm chemicals.
That's a perfect way to describe it.
So the neutrophils get there within an hour or two. They start killing bacteria and devouring debris. Then, a few days later, a second wave of cells called monocytes follow the same path, and they mature into larger macrophages to coordinate the heavy cleanup.
They bring in the heavy machinery.
It is an absolute masterpiece of logistics. But here's what blows my mind. For a long time, the scientific community assumed that once the bacteria were dead and the splinter was gone, the whole system just, got tired and stopped.
Yeah, the prevailing assumption was that inflammation was like a fire. Once the triggering stimulus was consumed, the fire just passively burned itself out.
Here's where it gets really interesting. Because in the late 90s and early 2000s, a researcher at Harvard named Charles Sirhan proved that assumption completely wrong.
He changed everything.
The final step, the resolution phase, isn't just the alarm running out of battery. It is a highly active, heavily regulated biochemical program.
Sirhan's work forced another massive paradigm shift. He discovered that turning off inflammation requires a distinct, specialized class of lipid molecules.
With great names, too.
They have great names: resolvins, protectins, and lipoxins. And fascinatingly, many of them are synthesized by the body from omega-3 fatty acids.
So to use the campfire analogy, it's not like letting the fire just run out of oxygen and fade away on its own. The body actually deploys a specialized phytochemical fire crew to actively spray foam on the embers and carefully sweep up all the ashes.
And that sweeping up process is vital. That biochemical fire crew relies on the macrophages, those large cleanup cells, switching their behavior.
How do they switch?
Well, when they first arrive, they are in a pro-inflammatory state, known as M1. They are aggressive. But the resolvins and protectins signal them to transition into a healing, repair-oriented state known as M2.
So they calm down.
They calm down, and in this M2 state, they perform one of the most elegant processes in biology, which is called efferocytosis. The word literally translates to taking to the grave.
Taking to the grave. Wow.
Yeah, the macrophages systematically engulf and digest all the exhausted, dying neutrophils.
They eat their own.
They have to. I mean, if a dying neutrophil just burst open in the tissue, it would spill all its toxic bacteria-killing chemicals everywhere, causing massive collateral damage and more inflammation.
Oh, that makes sense.
Right, so efferocytosis ensures the area is tidied up safely. Meanwhile, those same resolvins are signaling the blood vessels to stop recruiting new cells. The alarm is officially turned off.
Walking through this entirely changes how I view the whole process. And it perfectly clears up a couple of massive misconceptions that I think most people have.
Oh, there are so many misconceptions.
Misconception one being inflammation is always bad. But as we just saw, acute inflammation is a highly protective, fundamentally necessary repair process.
Absolutely necessary.
The problem only happens when Charles Sirhan's shutoff switch fails. Chronic inflammation is the bad guy, not acute. If you suppress acute inflammation completely, a simple paper cut might never heal.
You'd be defenseless. The tissue needs that initial wrecking ball and cleanup crew to rebuild.
And misconception two is that swelling always means you have an infection. But this entire 5-stage cascade can be triggered by a completely sterile injury.
Happens all the time.
You sprain your ankle playing tennis, there are no microbes, the skin isn't broken. But you still get physical tissue damage, which triggers the mast cells to release histamine, which starts the whole process. Redness, heat, swelling, pain, cellular response, all without a single bacterium in sight.
It's the exact same alarm system.
But, okay, I am genuinely struggling to wrap my head around something here. If this system is this incredibly orchestrated, perfect masterpiece of evolution, why is it so hard to treat medically? We have all these amazing drugs, but reading through these historical medical failures in the notes, it seems like whenever we try to intervene, things just go sideways.
It's a fantastic question, and it gets right to the heart of modern pharmacology. The difficulty lies in the fact that because this system is so critical to our survival, evolution built it with immense redundancy.
Redundancy.
Yeah. There are overlapping pathways, backup signals, and dual-purpose chemicals all over the place.
Meaning if one pathway fails, the body has 3 other ways to ring the alarm.
Precisely. Which is great for keeping a caveman alive after a tiger attack, but it is a nightmare for a modern doctor trying to design a drug to turn the alarm off.
I can imagine.
A really sobering example of this is the sepsis trials of the 1990s and 2000s. Sepsis is a life-threatening, body-wide inflammatory response to an infection. The alarm goes systemic.
Right, it's everywhere.
So pharmaceutical companies thought, quite logically, that if sepsis is driven by specific alarm chemicals, like the cytokines TNF or IL-1, we can just create targeted antibodies to block those specific nodes.
Like snipping the red wire on a bomb.
Exactly, but trial after trial failed. Some of the experimental treatments even harmed patients. The immunology community learned a hard lesson that is still taught today. You can rarely just block a single node in a redundant network.
Because it just reroutes.
Yes. If you snip the red wire, the body just routes the signal through the blue wire, the green wire, and the yellow wire.
Okay, so if we can't snip one wire because of redundancy, what happens when we try to block a bigger pathway? Because the notes use the drug Vioxx as a major cautionary tale here, and I know that was a massive scandal in the early 2000s.
Vioxx is the perfect example of the double-edged sword of this network. In the late 90s, scientists developed what were called COX-2 selective inhibitors. The goal was brilliant: block the specific enzyme that produces prostaglandins.
Prostaglandins. The chemicals from the very beginning of the relay race that cause the blood vessels to dilate and actively sensitize the pain receptors.
Right, so if you block them, you stop the pain and the swelling. And Vioxx did this incredibly well, especially for arthritis patients. And it had fewer stomach side effects than traditional drugs like ibuprofen.
It sounds like a miracle drug.
It became an absolute blockbuster drug overnight. But in 2004, it was abruptly pulled from the market worldwide.
Because it turned out it was causing heart attacks and strokes.
But I'm confused. How does fixing a swollen arthritic knee cause a heart attack?
Because of how interconnected the body's chemicals are. It turns out those exact same prostaglandins that cause pain and swelling in a knee joint are also quietly working in the cardiovascular system to regulate vascular tone and prevent blood platelets from clumping together.
No. Yeah. When patients took Vioxx to suppress the pathway in their knee, they were inadvertently removing the chemical safety mechanisms in their heart, triggering blood clots. The network is just too interconnected. You pull one string to fix the knee, and the cardiovascular sweater unravels.
That is terrifying. It really highlights why manipulating the system is so dangerous.
It's a delicate balance.
But sometimes we don't have a choice. During the COVID-19 pandemic, we saw what happens when the alarm system goes completely rogue. The recovery trial in 2020 showed that in the most severe COVID cases, it wasn't just the virus destroying the lungs, it was a cytokine storm. The patient's own inflammatory response got stuck in a feedback loop.
The 911 call was deafening, and the body lost the ability to trigger Sirhan's resolution phase. The lungs were filling with fluid and immune cells.
And the treatment that ended up saving millions of lives wasn't some targeted laser-precise drug. It was dexamethasone, an old, cheap steroid.
Dexamethasone is essentially a pharmacological sledgehammer. It broadly and aggressively suppresses the earliest stages of the inflammatory cascade.
It just shuts it all down.
It forcibly silences the chemical alarm when the body has lost the ability to do it itself. It was a blunt instrument, but in a cytokine storm, a blunt instrument is exactly what you need to stop the self-destruction.
Which brings us to the more insidious side of all this. We've talked about the acute alarm, the ankle sprains, and the sudden infections. But the notes highlight the Jupiter trial from 2008, led by cardiologist Paul Ridker. And this seems to have completely changed preventative medicine.
It really did. Ritker's work demolished the old-school idea that atherosclerosis, the hardening of the arteries, is just a simple plumbing problem where too much fat gets stuck in the pipes.
That's what everyone used to think.
Right. But he proved that cardiovascular disease is largely driven by a smoldering chronic inflammatory state in the blood vessels. He showed that patients drastically reduced their risk of heart attacks using statin drugs, even if their cholesterol was totally normal, as long as they had elevated levels of a specific biomarker called C-reactive protein, or CRP.
And CRP is a protein produced by the liver directly in response to lingering inflammatory signals in the body. So if your CRP is high, your internal alarm system is constantly humming in the background.
Humming, but never resolving.
So what does this all mean for us, for you listening right now? We've gone from ancient Rome to microscopic frog tissue to molecular Velcro and billion-dollar clinical trials. But this physiology isn't abstract. It's operating in your medicine cabinet right now.
Very true.
If you're listening to this and you've ever taken an over-the-counter ibuprofen for a headache, you are directly interacting with this microscopic cascade. You are chemically blocking those COX enzymes from making prostaglandins, literally interrupting the very first step of the alarm.
And if you twist your knee and throw an ice pack on it, you aren't just making it numb. By applying cold, you are mechanically forcing the smooth muscle around your blood vessels to constrict, fighting back against the vasodilation and the leaky pipes of the early stages.
That's amazing.
Furthermore, grasping the danger of chronic, unresolved inflammation is arguably the most important frontier in preventative medicine today. That smoldering alarm is the common denominator linking heart disease, type 2 diabetes, depression, autoimmune disorders, and even Alzheimer's disease.
Which is why all the health advice you hear today about prioritizing sleep, eating a balanced diet, and getting regular exercise isn't just generic wellness talk.
No, it's very targeted.
Researchers are intensely studying how those specific lifestyle factors actively lower baseline inflammatory markers like CRP in your blood. You're literally quieting the alarm system.
Which brings us to a final thought I'd love for you to mull over after this deep dive ends. If chronic inflammation, the failure of the body's system to shut off, is the root of so many modern diseases, perhaps the future of medicine isn't about finding better ways to block the initial 911 call of the innate immune system.
Like, stop trying to silence the alarm completely.
Exactly. What if, instead, the next major medical breakthrough relies on Charles Sirhan's discovery of the resolution phase? What if we find ways to safely turbocharge efferocytosis?
Oh, the cleanup crew.
Yes! Imagine a future where we don't suppress the body's vital early warning system, but simply give the microscopic cleanup crew the specialized tools they need to sweep away the cellular debris faster, resolve the tissue safely, and finally let the body rest.
So the next time you twist your ankle and see it swell up, don't just think about X-rays and jagged white lines. Think about the chemical alarms, the rushing blood, the microscopic Velcro catching cells in the current, and the devouring cells cleaning up the mess. The murky waters of inflammation aren't so murky anymore. We finally have the high-def cameras turned on. Thank you so much for joining us on this deep dive into the body's ultimate alarm system.
Until next time, keep questioning the world inside you.